5 first order linear differential equations as well as 2 algebraic equations. And in the second order corrections, we see that there is two mode, axisymmetric mode is there, where you see this LM value is 0, 0 as well as 2, 0. So LM 0, 0 value gives the spherical deformation and 2, 0 gives the quadruple deformation of the stars. So from the spherical deformation, that means L and M is 0, 0, we will get this equation number 20, 21 and 22, and it is an asymptotic solutions is there, and putting this P naught vanishes at the surface of the stars, we will and with the asymptotic behavior we will get equation number this 23. This del m is the mass correction due to the rotations, and also we will get the total mass energy of the rotating star as this equation number 25. Now for the quadruple deformation, from there we will get this equation number 26 and 27, but these equations, we can see these are the inhomogeneous equations, and so to get the homogeneous equation, the standard treatment is there, and we are following that, and to get these homogeneous equations, we will get this equation number 28 and 29, and from there this H represents the homogeneous part, and from there by putting that we will get this value of V2 H2, this is the perturbation part, and then this equation 30, 31, 32, 33 from there. And finally we will get the solutions as taking this inhomogeneous and homogeneous part in this form to get this value of VR and HR, where this stands for the regular solutions, and this AR taken as this one. So from using this, all this we can calculate by taking the 1 by RQ coefficient form, we can calculate the quadruple moments of the stars. And now all we know that as the rotation takes place, so some type of deformation takes place there, and for that deformation we will use the equation number 38 to get this eccentricity of the spheroidal. All this calculation, I again mention, all this calculation has been followed according to the Hartley and Thorne approximations. Now from the algebraic equations, from the two, we have got the two algebraic equations for these two parts of this M2 and PT as equation number 40 and 41. And now I just mentioned that the tidal deformability of the stars for the rotating stars is very, very important, because we have to study this tidal deformity, because the deformation takes place, and that this is the definition of the tidal deformity. This lambda is minus qij by epsilon ij. This qij is the quadruple moment, and this dimensionless love number, which is related to this tidal deformity, is taken as 3 by 2 lambda by r to the power 5. This dimensionless tidal deformity is nothing but this part, this lambda by m to the power 5. This is the dimensionless tidal deformity. So to calculate this tidal deformity, we use the standard Hinderer methods with that, and from there we will calculate the tidal deformity for our model. For our model, we got it. Now, all these equations has been formulated with this equation number 51, where this y is a vector with the 13 coupled differential equations, and this A is 13 into 13 square matrix with the two algebraic equations of P2 and M2 is there. Now here important point is that to solve all these differential equations, of course that equation has been solved with the numerically, it has been done, and in this case equation of state of the star taking a very important role, because this equation of state has been taken as the input to solve these equations, and so equation of state has taken as the input of this differential equation to solve it. Of course it is in numerically. And in this case, which type of equation of state we have taken? We have taken the equation of state which is the realistic equation of states. We have taken 6 realistic equation of state as an input of that, this WFF1, AP3, ENG, MP1, and MS1 and MS1B is there, and SLY equation of state is taken as the equation of state of the crust of the neutron stars. By taking all these 6 equation of states, actually we are trying to solve it. And the solution is taken with the series solutions of, by taking these series solutions, and we are finding up to the second order these solutions we will get by putting the boundary conditions. These are the boundary conditions to get that values, and finally we will take the mass. We will calculate the mass of the neutron stars after the integration is taken as from the center of the star to the boundary, as well as from the boundary to the infinity. We measure the mass. Now, after getting all these parameters, all these values, we are trying to plot it that is here we have for the 6 different equation of states are there, realistic equation of state, of course, and for there in the each graph we see there are two type of graph. In this right hand side graph is for the mass density curve is there, and here is the chi parameter, that is the coupling parameter is there. Here we are taken the coupling parameter with the different values. All we know that if we chi equal to 0, then FRT gravity will comes back to the GR gravity. So in this case, yeah, this is the mass density. Yeah, this is the mass and this is the density. Yeah, and here is, okay, is it?
This is mass, right?
Okay. This is the mass and this is the density. Okay, this part, and these for mass and the radius. So here what we see that this chi having different values, but what we see that this mass and the density actually independent of this chi values for each of the equation of state, realistic equation of states. But for the left hand side, what we see here, we see here when chi equal to 0, that means that is the case of the GR case. So it represents at the solid lines. So this is the last one. That means it is chi equal to minus 0.02. I want to mention there is some restriction of this chi value is there, and that was done by taking the observational data of the GW17 data as well as the massive pulsar data, and that was done by De Silva. That in this case the chi value having the restriction up to maximum up to minus 0.02. So that's why we have taken maximum value of chi equal to minus 0.02 is there. So in this case, so what we see from all these 6 graphs that the maximum mass of the neutron star for any equation of state of our study does not vary much with the coupling parameters, and as well as here what we see this maximum mass does not vary there, and this mass and density is actually independent of this chi. And also from this compactness versus mass relations, what we see here in this case, whenever the mass is less, then the variation of this chi is significant. But whenever mass increases, for the higher mass, this variation actually it is nearly to be negligible. So in each of the cases of the 6 different equation of state, we see the same type of phenomena. Now again, for the rotation of the mass corrections, what we see here, and as well as the rotational binding energy correction with the function of mass, what we see here, for the lower masses, this variation is greater, but whenever we move to the higher masses, then this chi dependency actually nearly to be vanishes, very small in all the cases we see. And for the change in the radius due to this rotation and the eccentricity, I want to mention here that we have taken the order up to the second order of the rotations, and that calculation is very complicated. So we have done this for this FRT gravity. Earlier many scientists have done for GR as well as for FR gravity, but we are the first to do this in FRT gravity for this calculation up to the second order I just mentioned. So that's why we get this change of this radius due to rotation, we get this type of curve. And here what we see for the lower masses, we see the significant changes are there, but for the higher masses, that changes is not significant. And also for the quadrupole moment mass, what we see here, we see that whenever the mass is increasing, this quadrupole moment is increasing up to a certain value, but after that it value is decreases. And for the moment of inertia with the mass, we see here it is nearly independent of these chi values for all the different equation of states. And also for the tidal love number case with the function of mass, what we see here, again for the lower cases, it has a increasing value, after that it has decreasing value, but for the higher masses case, again there is no significant changes with this chi. And for the very important part is that which is related with the I love Q relations, that means the dimensionless of the moment of inertia, but the dimensionless of the tidal love number. What we see here for each realistic equation of state, we see this variation is nearly negligible. So all these cases for different chi values we see there. And also for the dimensionless quadrupole moments, what we see here, again for the dimensionless love number, all these cases it is nearly independent. So that implies that this I love Q relations does not depend on the coupling parameter, and that is the most important point I want to mention here, that again that earlier Hartley and Thorne proved it for the GR, that I love Q relation will be valid for that, and many scientists have done in FR gravity, but in FRT gravity we have shown this I love Q relation, that it is also valid for this FRT gravity. And also equation of state independent parameter, that means if we put here the GR value, 6 equation of state has been put here, all these cases that it is independent of the equation of state. So we see all the curves nearly coincides, that means for all the equation of state have the same type of result, so it is independent of the equation of state. So I love Q relations is hold for different equation of states. So this is, in conclusion, what we have done is that here in FRT gravity, by using the Hartley-Thorne formalism, we have calculated that mass, radius and the moment of inertia, as well as rotational effect is there, the change in the mass, radius and the binding energy eccentricity, as well as the tidal deformity and the tidal love number and quadrupole moment. And most interestingly, that in the second order of the rotational effect, that means the change in the radius, binding energy, which cannot be done in the first order rotations, and that is show larger deviation in the general relativity in the lighter neutron stars, though Hartley and Thorne have done in the second order rotation in the GR, and we have done it in this FRT gravity. And also the first order quantities like the moment of inertia shows the minimal deviation in GR, and we have shown the I love Q relations in FRT modified gravity is that. And most importantly, the matter geometric coupling parameter has a greater impact on the lighter neutron star rather than the heavier masses. So this is our conclusions. Thanks to all everybody.
Any question?
So, quite a fundamental question. In the theory F of R and T,
Yes.
The covariant law of conservation is violated. It's obviously, yes. And because of this, should exist some restriction for the parameter chi.
Yeah.
Just from general physics.
That
could you give some comments about it?
Yeah, of course, sir. In there, that chi parameter limitations actually has been coming from the observational data.
Yeah.
The data of the DW17 data of the massive pulsars. From that data restriction, De Silva has shown that this coupling parameter value has some restrictions. That value is maximum up to minus 0.02. De Silva and his group has been done by taking that observational data from the GW17 data.
Okay.
Yes.
Okay. And it's not question, but I just didn't catch what you mean when you speak about realistic equations of state. Because as I understand, you consider just polytropic equation of state.
Yeah.
But
yes.
polytropic equation of state is the simplest and model, and in fact, it's not so realistic. Yeah.
I just want to mention that these realistic equation of state has been done actually according to Pauli and Pani. Pauli and Pani have done that by taking the piecewise polytropic equation of state. Piecewise polytropic equation of state.
So
we are using that.
Polytropic.
Yeah, exactly, sir.
Yeah.
Piecewise polytropic equation of state.
I don't know
Yeah.
if it's possible to say that it's realistic, because I don't know. Maybe.
So
Okay.
it was done by Pauli and Pani earlier. That but by using that piecewise equation of state, therefore from that that realistic equation system has been formed.
Well, and once more,
yes.
which is central energy density, matter density?
Yes.
Which central mass density we use?
Yeah.
You use?
Yeah.
Which one? Which value for?
No, we will see. There are 6 equation of states. Yeah, that 6 equation of state having.
I mean mass density in
Yeah.
the center of neutron star.
Yeah.
Which value you use?
That value of the order of 10 to the power 15 gram per cc.
10, 15.
10 to 15 gram per cc.
Thank you.
In one of your slides about the variation of tidal love number, one of the equation of state was showing a different trend. Can you just go?
Yeah.
I think before this. Yeah, this one.
Yeah.
So each one is an equation of state, right?
Yeah.
Why is the last one giving a different trend?
Yeah. Actually, this one gives the different. But what happens, as I mentioned, that whenever for the lower masses, it actually increases. It increases, and up to some distance, after reaching the maximum one, it actually decreases. So if you enlarge it, it will look like this type.
Okay, but others all look kind
Yeah.
of same. That's
Yeah,
why.
then scaling changes.
Scaling, okay.
Okay, so no more questions. So let us thank speaker Professor Mehdi Kalam for nice talk. Session is over. So let's organize. Hopefully it is tea break now.